Okay. We'll start in, say, just 1 more.
I think the volume is little low from your side. I don't know.
Okay, let me. I think there is a way to adjust the input level. Is it better now?
Yeah, it's better, I guess. Yeah.
Okay, so let's start. This will be the final session of the workshop, and we'll end with support vector machines. Right. So the agenda for this session will be quite similar to what it was yesterday and today morning. So we'll very briefly look at the theory for hard margin SVM. This is more for those who are from previous terms. Current term students would have already seen this several times. So this is just a very quick recall for them. For the others, this might be relevant. And then we look at implementation of hard margin SVM. And then we'll go into soft margin SVM. In very brief look at the theory and followed by implementation, right? And finally, there'll be some closing remarks, and with that, we'll end the workshop. So please follow this URL as usual. The slides will be uploaded later today. The svm.ipy note ipynb, right? So that particular file is what we'll be using. It should look something like this. So if you can open it, and those who are interested in coding along, please do so. This lab will look something like this. Okay, so let's start with the theory part of it. Very briefly, as I said. So morning we looked at perceptron. So I think we would have discussed what it means for data to be linearly separable and what it means to have gamma margin and so on, right? So you have infinite number of valid classifiers, right? So perceptron is one of them. Or perceptron returns one of them. Now there is obviously the question of, is that classifier the best possible classifier? And naturally we have this question of what is good, right? So what is a good notion of best? When we say, is this a best linear classifier possible, what do we mean by it? So we need to refine this notion of best, or at least clarify what we mean by best before we can move along, right? So this is where the idea of margin comes in. So the margin very roughly can be understood as the distance of the nearest data point from your classifier, right? So if your classifier is a line, the solid line here, if that is your classifier, then the margin can be said to be roughly speaking, right? So it's not exactly the margin, but it's fairly accurate statement. It's the nearest, it's the distance of the nearest point to the classifier. That is the margin. So in this case, it will be the distance between the solid line and this one of the two dotted lines, right? So that will be the margin. So small margins don't then generalize well. And an example for that is given here. So if you start testing your data set, if you start testing your model on test data points, on unseen data points, then if the margin is small, then there is a possibility of, there is a greater chance of misclassifying unseen data points. So for example, these white color data points here, they are actually misclassified by this classifier that you have here, right? So assume that these two white points belong to the red class and this particular white point belongs to the green class. So if that is the case, then it classifies it correctly. But on the other hand, if these two white points actually belong to the green class, right, then your classifier is sort of misclassifying them, and the problem is the margin is very small, right? On the other hand, if you have a wide margin, so I'm using the same data set here, I'm not changing the data set at all. Only thing is that I'm moving from a smaller margin classifier to a wider margin classifier. Larger margins, they kind of generalize better. So that's the whole intuition behind this notion of best, right? We wanted to define what a best linear classifier could be, and what we are saying is that our notion of best linear classifier is one that has a large margin because it generalizes better. Okay, so that's the idea that we'll be using. So the next step then becomes computing this margin, and for any linear classifier W, you can find a margin associated with that linear classifier, right? So given a data set and given a classifier of the form W transpose X equal to 0, you can compute the margin, and that margin turns out to be 1 by norm W, right? So this is just the algorithm. I'm just listing it quickly here. So find the point closest to this W transpose X equal to 0, this line, and if you, provided you make some adjustments to your W, you can show that the distance of the closest point from the classifier is 1 by norm. Any questions? Okay, right. So note this point here that W transpose X equal to 0 is the classifier, and the closest point lies on this line W transpose X equal to 1. Right. So we call this the supporting hyperplane, as you all should already know or recall from your lectures. So the closest point lies on one of these two supporting hyperplanes. Here I have only written down W transpose X equal to 1. Correspondingly, there will be a W transpose X equal to minus 1. Right. So these are called the two supporting hyperplanes, and together, they define whatever we are going to be working with, right? So we have computed the margin, and that is 1 by norm W. So now the question is, we need to maximize this, right? So we need to maximize this, and it's not just a maximization problem. There are also some constraints. It's not an unconstrained maximization problem. There are some constraints associated with it, and the constraints are that the points are linearly separable, right? So they should lie, in this case, we say that they should lie beyond the margin. Or another way of putting it is that they should not violate the margin. Okay, so they should not violate the margin. So meaning W transpose X should be greater than 1, right? Or to be more precise, W transpose X into Y should be greater than or equal to 1. So equal to 1 would mean they lie on the supporting hyperplane. Greater than 1 would mean they lie beyond the margin, right? So that is what we have in terms of inequalities, and this inequality should hold for every point in your training data set. Okay, we don't know anything about the test data set. This inequality should hold for every point in the training set. So if you put the constraint and the objective function together, what we have is what is called a max margin classification setup, right? So we have a classification setup where we are trying to maximize the margin subject to some constraints, right? And these classifiers are typically called max margin classifiers because that's what they try to do. They try to maximize the margin. Now max of 1 by norm w is equivalent to minimizing norm w by 2 or norm w square by 2. This 2 is added for convenience, and the norm w square is the square of the norm is taken because it makes it a smooth function to differentiate, right? So it's easy to differentiate if you don't have the square root signs. So that is why we add the norm w square by 2. Okay, so that is the setup. We can't now directly go on up. Yeah, any questions?
So yeah, so I am in fact forgotten the concepts. Can you just explain the constraint of W transpose T x into Y I being greater than equal to 1?
Yeah, so the W transpose X equal to 1 is this line, right? This dotted line.
Right, sir.
So what we are saying is that we are in a linearly separable setup, right? So data set is linearly separable, and for a linearly separable data set, there is something called the margin associated with it. So margin, you can think about it as how close the data points are to the classifier, right? So the expectation is that all the points in the data set are beyond the margin, right? Or they don't lie anywhere within the margin, because we have already defined that this margin is equal to 1 by norm w, where that is nothing but the distance of the closest point to this line. Okay, so now every point, if you take in the data set, will be at a distance greater than d star. Do you agree on that
Yes, sir.
point? Okay, so everything will be at a distance greater than d star. So if you actually do some small bit of math, you can see that the distance of a point is nothing but w transpose x by norm w.
Right.
Okay, so the distance of a point is w transpose x. The w transpose x is nothing but the projection of a point on w. You divide by norm w to get the distance, signed distance in some sense, of the point from the classifier. So we are saying w transpose x by norm w is greater than 1 by norm w. Okay, so this norm w gets cancelled off, and you are left with w transpose x greater than 1.
Right, sir. Got
Okay,
it,
so
sir.
this yi comes in because for the red color points, w transpose x will be negative, and yi will also be negative. It will be -1 for those points.
Clear, sir. Thank you.
Okay, yeah. So that is the optimization setup. We are trying to minimize norm w square by 2 subject to these inequality constraints. So there is a lot of, I request all of you to go back and watch the lectures of uh, week 10 in the just concluded term of MLT, for those of you who have not seen those lectures. So there is a lot of theory that has been developed to arrive at this slide. Okay, so I'm just presenting the final version of a lot of math which happens, very interesting math. So those of you who haven't seen this, please go and take a look at it. Right, so what we have on the left hand side is the problem we are trying to solve, right? It's minimize norm w square by 2 subject to some constraints. Now we can actually claim that this is equivalent to this problem here. Okay, again, I'm not going into the details because that's not the scope of today's session. That's not the agenda, right? So only thing you need to understand is that this is the usual Lagrange multipliers that are brought in, right? So alpha I, one alpha I for each constraint. So moment you bring in the Lagrange multipliers, you get a form like this. Okay, and this is called the primal problem, and corresponding to it, you have what is called the dual problem. By so roughly speaking, you can think about it as swapping the max and the min values, right? So this is min over w, max over alpha. You have just swapped it here to get the dual problem of max over alpha, min over w. So roughly speaking, you can understand it like that. Now this equivalence is a strong condition which holds good only for certain class of optimization problems. uh, so the functions have to be convex, the constraints have to be convex, and so on, right? So we are not then going into this, but what we need to focus on is this right hand side, right? This thing which is called the dual. Okay, and this is what we'll be optimizing. Okay, so the summary of the slide is that we want to optimize this. We want to maximize the margin. That's the left-hand side part of it. That is equivalent to maximizing this quantity here. In this quantity, this expression or this problem is called the dual problem. So that is the main takeaway. And how we arrive at this, in case you are not aware of it, it doesn't matter. This is this can be learned at a later stage also. Okay, any questions so far? The current term students will, all this will be very familiar to them because they just completed this. But for old term students, any questions?
In the previous slide, whether it is necessary that both the side the margins would be equal.
Yes, right. Yeah, that should happen, right? Otherwise, what will happen is if you kind of move the solid line, say, to the left, closer to the red color data points, the closest distance will change actually, right? So this point will become, so currently this point is anyway close to it, but this imbalance will be created, right? So on both sides of your classifier, you must have the same distance, and that is what we call the margin.
Okay, sir. Okay.
Okay. Yeah, I know it's not a very convincing explanation, but for now, take it that this is how it is. Okay, maybe at a later date we can discuss it in more detail.
Okay, sir. Okay.
Okay, geometrically, you should have one point on either side that is at the same distance from your classifier. Okay, any other questions regarding this primal dual business?
I have a question. So here you have given both the primal form and the dual form, right? So typically you'll solve primal if it is in lower dimension or dual if it is in lower dimension. So how do we know whether to solve the primal problem or dual problem on the dimensionality of the problem?
Okay, so dimensionality is one thing. In the case of SVM, it's not just dimensionality that helps us in the case of dual, right? So we solve the dual for SVMs because that offers few other advantages. So if you wait for a while, we'll see that the dual form of the SVM includes some information about what are called as kernels. Again, something. So kernels we briefly touched upon in the previous term, but we didn't explore in this detail. So that
Oh,
form
yes,
is
sir. Yeah, so nonlinear becomes linear in the higher dimension by applying kernels. Okay, got it. Yeah, I mean, yeah,
right.
I'm a former term student, so
Right,
now
right.
I'm able to recall. Yeah, thanks.
Okay, so any other questions? If not, we'll move on, right? So okay, so now this is the dual, right? So this is the dual, and what we do is we have a max outside, and inside we have an unconstrained problem. So we can freely take the derivative, set it to 0, and find W to be a sum of a linear combination of your data points, right? So it's a linear combination of data points weighted by your Lagrange multipliers and the label yi. Again, don't worry too much about how all this is obtained because that will take some time to explain. Now, if you do some algebra, then it turns out that you can express the dual, the weight vector, right, in this form, right? So the weight vector is actually equal to the data matrix, right? The data matrix X, the label matrix Y, and these Lagrange multipliers alpha. Okay, so again, it's a bit of algebra, nothing more than that. What we are essentially saying is that your weight is the linear combination of your data points, and your labels also enter the picture in the form of this diagonal matrix capital Y. Alpha is just a vector of Lagrange multipliers. Okay, so this is obtained by solving this unconstrained problem. Once you do this and substitute W back into your dual, this is what you get. Okay, so this is where we'll start our collapse. So note that after doing a lot of algebra, we end up with something like this. This is called the dual problem, or this is the final form of the dual problem, and this is what we would have to maximize if we want to get the value of alpha. Okay, any questions about this particular slide for the previous term students? Okay, so this is what we'll be maximizing. I know it was a very fast
Sir, go to
introduction.
previous slide.
Previous slide, okay.
This one. Yes. So this W is calculated from this expression, Lagrange expression, right?
Yeah. W is calculated. So we have this box is there, right? The box that I've shown here. So
Yes.
that optimization problem within that box is an unconstrained problem, right? It's just minimize W f of W.
Correct.
So what you do is you f dash of W equal to 0. That's what you do. So you take the derivative of f, set it to 0, and from that you will obtain W to be sigma alpha I xi y.
Just the normal derivative, right?
Yeah, normal derivative. So you will get, so if you take derivative, right, you will get 2 into W, for instance. This is W transpose W, 2W, and this will be just sigma xi yi, alpha I. So W equal to sigma alpha I xi y. Okay, and you are just rewriting it as xy alpha. You are just vectorizing the whole thing. So if you vectorize this, it's easier for you to compactly represent the whole thing. Okay, so what you need to take away is that if you're trying to solve some optimization problem for SVMs, and instead of solving the original optimization problem, it is easier if you solve this different kind of optimization problem, which is equivalent to the first one. Okay, so we are not losing anything in this process. We are just, by using certain mathematical tricks, we are converting the original optimization problem into a form which is, I would say, in some sense, say better than the original one, right? So it's solving this is a good. Yeah, so I muted one of you. If you have a question, please let me know.
Yeah, sir. Could we neglect one in this expression, sir? Alpha transpose 1.
Yeah. So 1 is nothing but a vector of ones. It's
One,
like,
sir.
yeah, 1 is a vector of ones. So it's like there are n ones and it's a vector. What we are saying is it's sigma alpha I, right? So you want to sum all the elements of alpha vector, alpha 1 plus alpha 2, so on alpha n. Instead of writing it as sigma alpha I, you are writing it as alpha transpose 1 as the dot product of alpha and np dot ones, right? So we looked at np dots ones, right? That one.
Yeah, thanks.
Basically, sir, in this unconstrained optimization problem, we are basically taking derivative, getting W, then using that value in the optimization and getting out of this expression, right? Maximization alpha transpose 1, right?
Exactly, yeah. So we minimize this and we get W as this. We plug it back into this so that we end up with this. Okay, so keep this expression in your mind. This is what we'll be optimizing. And
so, sir, actually, we are here to find W. But what about alphas? Means we can calculate alpha also, or it will be given.
so alpha is the one so you are correct. We are here to find the W, but the moment you find the way you have done it is you have expressed W in terms of the alphas, right? So note that X and Y are constants as far as the problem is concerned. They are already given to you. So figuring out what the W is now equivalent to finding out what the alphas are. Right? So if alpha is known, then W is known. So I am solving for the alphas. Moment I know what alpha is, I can use this xy alpha expression to find out what W is.
Okay, so we will find alpha. Actually.
Yeah, we are going to solve for the Lagrange multipliers, right? Or KKT multipliers, whichever is.
Yes.
Okay, so is that clear now what we are trying to do? Okay, so Okay,
Yes, sir.
I'll come back to support vectors towards once we solve the optimization problem. So that'll be better.
Sir, one
Yeah,
question.
yeah.
So in the previous slide, we had this 2 in the denominator, right? So that I think is just because of mathematical convenience, no? Because when we do the derivative, we'll get that cancelled out with the other 2, right?
So that 2 is a, so we start off with this 2, right? So
Hmm.
we start off with this 2 and it kind of sticks with us all through. So it's, so that
Okay.
it's an offshoot of, yeah. So initially we added it for mathematical convenience and it
Hmm.
remains for that reason only.
Yeah, that is what. So, I mean, as far as the optimization problem itself is concerned, I don't think the 2 is going to give us a different result, no? Even if we do not have the 2, we'll still get the same vector, right?
So if you scale the whole thing by 2, then yes. So if you say
Okay.
2 alpha minus alpha transpose whatever,
Hmm.
let's call this q alpha, then that's fine. But
Okay.
can we just remove this 2 and will it still give the same result? I am not very sure. We have to look into
Okay.
the math little more in detail.
Sure. All right. So this is from the previous, the denominator 2, which was there in the norm w squared, and the denominator was 2. So that is being carried over here as well. That is what.
Yeah, that is being
Is that
carried
right,
over.
sir? Okay. Sure, sir. Thank you.
Yeah. Okay, so in case someone wants little more idea into how this is formulated, you can, so norm w square is nothing but w transpose w, right? So w transpose w, you plug in xy alpha, you will get this alpha transpose y transpose x transpose xy alpha, right? So this whole thing is nothing but w transpose w, if you can see that, and this is norm w square, right? So this whole term is actually this term here. Okay, and so it's actually very simple algebra. It looks hard because we have not gone through the steps, so that is the only thing. Okay, so we are not trying to solve this. That's what we have to keep in mind. Okay, let's get started. So you have some data set given to you, right? So we won't be generating our own data set. In this case, it's some data set that is already given to us. So let's first look at what that data is, right? So X is a data matrix of shape D cross N. So let me go ahead and see what the shape of X is. X is 2 cross 20, right? That means there are 2 features and 20 data points. Y is a label vector of size n. So Y's shape should be 20, right? So it is either 1 or -1 for each of these 20 data points. And if you want to visualize or have a quick look at it, so the first 10 are label 1 and the next 10 are labeled -1. Okay, so that is all with respect to X and Y. Let me just print it.
Sir,
Copy of it. Yeah. Yes.
sir,
Sorry, I didn't get your question. Uh, Sorry, I'm
can
not able to hear you properly.
you blink?
Collab link is there in that,
Please share the collab link.
is there in this tiny.cc/mlt_workshop. You have to go to day 3 and you'll find the SVM notebook there. Okay, so yeah, so that is understanding the data. There's nothing much to understand about the data. So let's go ahead and visualize it. We have to draw a scatter plot, and addition to just plotting the scatter, we have to look at the colors of the points. We have to assign all +1 points as green, and we have to assign red to all the data points which have labeled -1. Okay, so let's first do the plotting and then take care of the rest. So plt dot plot dot scatter, right? So plt dot scatter, X is the data matrix. So what is the shape of X? X is D cross N, right? 2 cross 20, which means the first column is corresponds to the X values. First column corresponds to the X values, and the second column corresponds to the Y values. Let's just, okay, this we have not yet imported it, so it's throwing an error. Let's go ahead and import it. Import matplotlib. So we import matplotlib, and as before, what I'm going to do is I'm going to set some parameters here. In particular, I want my figure size to be 10 cross 10 or 8 cross 8 maybe is better. And I also want my font size to be say 15, right? So the font of size. Okay, so that is just something that I'm used to doing.
Should it be 0 comma colon and 1 comma colon?
Okay.
It's 2 comma 20, right?
It is 2 comma 20 t cross n.
Yeah.
You are
We
right.
need
You are right.
we need all the columns.
You are right. So once again, so d cross n, we need 20 points, right? Okay, just 1 second. I'm getting a bit confused. So
That's right. It should be 0 comma.
0 comma colon, is it? Okay, I think
It's the transpose of X as well.
It's D cross N.
right. Okay, you are right. Okay. 0 comma colon and so basically we are looking at each row as each first row corresponds to the X values and second row corresponds to the Y values. Is that right?
Yes, sir. Yeah.
So let me just write it down because I got confused a bit. So B equal to 0 will be the first row, the X values, and second row, Y values. It's D cross N. So each row corresponds to one feature, and therefore this is the way it has to be. Okay, thank you for finding that out. So this is just a scatter plot. Yeah.
So in the first block of code, there's a transpose. If we remove that, we can go back to the earlier method.
You are right. Yeah, you are right. So this transpose was added because we want the convention that we followed in the current term was the data matrix is D cross N. So that's why, but you are right. If we had used N cross D, then the columns would have been the X values and Y values. Okay, so sorry for the confusion. This is for our D cross N data matrix. Okay. Okay, so this is just the scatter plot. We have to now color it green and red. So what I'm going to do is I'm going to define a color matrix for this. Okay, color matrix, and so let me also add this. +1 is green, -1 is red. So if you look at indexing, right? So -1 would correspond to the last element of a list, right? So I want red to be the last element of a list, and 1 should be the second element of the list, and the first element is basically some dummy value, right? So it could be some dummy. So do you see why I am doing this? It's not clear. It will become
Yes, sir.
clear.
This is clear. Yeah.
It's clear, right? Okay, so let's just go ahead and
Because
do
the
this.
indexing is starting at 0, no? So wherever it is 1, we'll be picking the green color, right? And
Exactly.
wherever it is -1, we'll be going to the last one, which in this case is red. So that is
Right. Exactly, right? So that is why we are doing this. So now if I plot the scatter plot, in addition to that, if I add this argument C stands for color, right? So C stands for color. What we are doing is we are not giving color individually one by one, but instead we are giving the color as an array. If you are plotting 20 points, then for each of these 20 points, we need to give a color, right? So Y is of size 20. It corresponds to the label of each of these 20 points. And color of Y will be nothing but the color for each of these points. So let me just run this. And so it is not colored. So I'll just show you what color of Y is. Okay, so color of Y looks something like this: green, 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 so on, and then red, 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 red. Okay, so what we have used here is the ability of NumPy to allow NumPy arrays themselves as indices, right? So Y is a NumPy array. That NumPy array is indexing into another NumPy array, which is this color array. Okay, so because of this facility provided by NumPy, we are able to do this. Okay, so I hope this is clear how we have visualized this using a scatter plot. Okay, so once this is done, there's a question that we are asking: is this linearly separable or not from inspection? If you just inspect it, can you tell me if it is linearly separable or not?
Yes,
Yes, it is. Yeah.
it
Okay,
is.
it is right. So by inspection, we see that there is this slender line that's going to go right through these two. Okay, so it is, at least from inspection, we are convinced that it is linearly separable. But here is a question: assume that there are like so many points and some high dimensional space where you can't visualize them also. Is there another way to determine linear separability? And this is actually one of the questions that was asked in discourse this term, if I remember. So
I think you can use PCA or something like that.
okay, PCA maybe not, but something else, something that is related to what we have seen so far in this workshop.
sir.
You
May I
can
answer
use
Yeah,
that?
sure.
Perceptron.
Perceptron doesn't converge.
Yes, exactly.
From
Yeah.
Oh, right, that's a good point. Right? We'll try to do that very quickly. So there will be a refresher for whatever we saw in the morning, kind of bridging the two together. So I'm not going to explain the code too much. So let's quickly go ahead and do it. So let's start with a set of zeros. Okay, so that's the initial weight vector. Dimension is D. Is D not defined? Yeah, D is not defined. So let's define D. D comma n will be x dot shape, right? So make sure we define that. So you start with a set of zeros, and then so I'll explain this if not in too much detail, but still. So while uh, while not all the points have been classified correctly by the perceptron, okay, if there is some point on which we are making a mistake, okay, if there is some point on which we are making a mistake, it should be less than or equal to 0, then use the update rule of xi yi, right? So okay, and then you increment I, right? What is I? I is nothing but something that's going to cycle through all the examples. So if your I becomes n, which is the last example, then you have to cycle back to 0. Now run this and see. Okay, there is a should be the ith data point. So okay, so what can someone tell me, or does anyone see what we have done so far and how we have shown that it is linearly separable?
If not linearly separable, it would not have ended. Go to infinite loop.
Exactly, right? So that's correct. So if it had not been linearly separable, then it would have just kept on iterating, right? Because there some mistake or the other will keep on that mistake will be made forever, right? And perceptron would have never converged. But in this case, because the loop has ended, that means that the data is linearly separable, right? So we have just shown that in a very computational way that the data is actually linearly separable. So did all of you get this part? If not, you can revisit this later. Any questions about this piece of code? In case you have not seen this part, I'll just let you know what this is. So np.all is true if everything inside is true, right? So for example, np.all of true comma true will be true. But the moment even one of them becomes false, np.all is going to return false. Right? So what this condition is saying is that if there is even one misclassified data point, go inside the loop and terminate the loop when there are no misclassifications. Right? So that is what the while loop's condition is saying. This is just the perceptron update rule, right? And nothing else. Okay, so anyway, we have found one classifier that is 6 comma minus 2, but that is not what we are really looking at. What we need is to solve the SVM dual problem. So the first things first, so we need to compute this matrix Y that appears in the dual problem. So can someone tell me how you can compute Y in NumPy? I need to compute capital Y.
Reshape it also.
I can. Well, we can.
np.diag
Okay, that's good. np.diag of what?
of y.
Okay, that's good. Right? np.diag of Y. We just need the. So what is this? This is nothing but a diagonal matrix made up of the labels of the endpoints, right? So let's visualize. I mean, let's just print Y and see what it looks like. This is a 20 cross 20 matrix because there are 20 data points, and the first 10 diagonal elements are going to be ones, and the rest of the 10 diagonal elements are going to be minus ones. Okay, so Y dot shape 20 cross 20. Okay, so we now have one matrix in place. X is anyway given to us, so X capital X we already have, so that is sorted. All that remains to be done is to compute this matrix, this whole thing I've called Q. Q is Y transpose X transpose XY. Okay, that is what I call it as Q because it's kind of.
I didn't understand the y part. Why it's diag like
Y is this, right? So capital Y is diagonal matrix made up of the labels on the diagonal. You are asking why this capital Y is diagonal? Is that your question, or your question is?
yes.
So that is because of this some algebra here, right? So your W is sigma alpha I xi yi. Now what you're doing is you are breaking this matrix down into y x times y. So this is actually x into y, where y is this diagonal matrix. Okay, so it's just linear algebra, matrix multiplication, nothing else. Okay, if you, or rather I'll come this way, if you multiply x and y, you will get this matrix here on the LHS, right, or on the RHS rather. Is that okay?
Okay.
Okay, so that is y, and now we have to compute q. So what should q be? Can someone tell me how q will look like? Okay. Q will be very simple actually. Y transpose x y transpose, right? So it will be y transpose x transpose
XY.
y. Okay, so that's all. That's all y is. That's all q is. We have computed q. Alpha is anyway the unknown which you have to compute, right? So once you do these two things, you have the objective function in place. So that's what we'll be computing now, right? Now one small point, since SciPy's optimization routine is minimized. You remember we did this in Friday's session. So SciPy gives you something to minimize function. So what we have is, on the other hand, a maximization problem, right? Whereas we have a maximization problem. What we'll do is we'll convert this into a minimization problem without losing the without losing anything, right? So we'll just take the negative of this objective function, and that would be half into alpha transpose q alpha minus alpha.
So this Q will be an n cross n matrix, right?
Q will be an n cross n matrix, yeah. Okay, so wait, just give me a second. Why is this? Is all this appearing like this? Just give me a second. There seems to be some rendering issue. I don't know why.
Maybe it is from server side.
Right. Yeah, I think so. I hope so. It's not. Right. There was some issue with this one. Okay, so where were we? We were in the Q part. So Q is an n, yeah, as you said, it's an n cross n matrix. Alpha is a 20-dimensional vector, or rather, in terms of numpy, it's vector of shape 20, comma, right? So that is alpha. So let's go ahead and compute its function f. F of alpha is to be nothing but 0.5 into alpha transpose. So alpha, you don't need the transpose here because it's just a vector. So this should work. Alpha q alpha. Okay, minus. So how do you express this alpha transpose 1? Can someone tell me what it will amount to, alpha transpose 1?
Alpha transpose NP once.
Okay, is there any other way you can write it? That is correct. What you told is correct.
NP dot sum of alpha.
Exactly, right? So NP dot sum of alpha, or you could just leave it as alpha dot sum. Okay, so both of them are the same. Alpha transpose 1 is also correct. Alpha transpose NP dot 1, that is also correct. But we'll just stick to this one here. So that is all with respect to defining the function. Okay, so once you have defined the function,
can you please tell where you got the Q? Like Q, how you calculated Q?
Yeah, Q is nothing but this matrix here. Y transpose X transpose XY, I call it Q.
Okay.
Okay, so Y transpose X transpose Y is Q. So the reason I call it Q is because this thing, this whole setup, right? It's a quadratic programming problem. Okay, so you can search for this in Wikipedia. It's a particular class of optimization problem called quadratic programming problem. That's because if you expand this out, right, you will see that alpha I, alpha j terms come up. They're all degree 2 terms. If you expand it, this is actually, so let me perhaps think it might, since we have a lot of time, not even 4. So we just expand it. Can be expanded as follows. So you can write this same thing as, so let me expand it in terms of the scalar values, right? So there are n data points. Okay, there will be, so there are alpha 1 to alpha n, one for each data point, one Lagrange multiplier for each point. So this will be just sum over alpha I. Okay, that is the first term. Alpha transpose 1, it results in this. Okay, the second term is 0.5, okay, into alpha transpose q alpha is actually a double sum. If you expand it, you will see that the double sum over limits I and j. Okay, so over limits I and j, what is that? It is alpha I, alpha j, okay, qij. Okay, so this objective function is actually quadratic in alphas. So when I equal to j, you will get all these alpha I square terms. So that will be the diagonal of the matrix Q multiplied by alpha I square, right? So that, and then you will have the off diagonal terms also, alpha ij, alpha I, alpha j, qij. So this is, because this is quadratic in nature, it's called a quadratic programming problem. Okay, is that clear?
In the code, this alpha dot sum, I didn't. It should be, how's that equivalent to NP dot 1?
Okay, so alpha dot sum, where is it? Yeah, so alpha dot sum is equal to the following, right? So what we are saying is, let's take a concrete example. Let's say alpha is 1, 2, 3. Okay, so now of course it is 20 it has 20 elements, but this is just an example. So alpha dot sum will be just 6, right? So that is sum of the elements of alpha. That's what we want. This is also the same as np dot ones of 3, right?
Clear, sir.
So that is what both are correct ways of writing, but we'll just stick to alpha dot sum. Okay, so we are trying to solve a quadratic programming problem, and we have found the objective function. Only thing that's remaining is the constraints. The constraints here are actually very simple. They are just bounds. When I say a bound, it's just that alpha is greater than or equal to 0. For every alpha I, that value should be non-negative. That is all the constraint is, right? So this is another feature which makes the dual part of the problem very appealing, because in the, if you look at the primal problem, right? So let's go back. If you look at this primal problem, look at the constraints that you have it, you have linear constraints in W. So still it's not bad, but they're of the form W transpose xi yi greater than or equal to 1. Slightly harder looking constraints compared to the constraints in the dual problem. Dual, you have only alpha greater than or equal to 0, and that is another reason why the dual is kind of appealing for us, right? And it's easier to solve. Okay, with that, all these things in place, we'll now finally see how to optimize. So let's look at importing what we require. So from SciPy, we have to import stuff. Let's see what we have to import. Give me a second for this.
Optimize.
SciPy dot optimize it. So SciPy dot optimize. Import minimize. I have my reference collab open, so I'll probably have to look at it. Okay, for now, we'll stick with this. So from SciPy's optimization routine, we are importing minimize. Okay, so okay, so it's actually, this is correct. It's not wrong. What you said is not wrong, but optimize, we'll import optimize itself from SciPy for certain reasons that will become clear soon. So what SciPy does is it will try to minimize this function, but since the methods that we'll be using are numerical methods, they'll be somewhat iterative in nature, right? So it needs some initial value to begin with. Okay, and we are going to give zeros as initial values. So what dimension, what value should I put in here for alpha init?
20.
Okay, 20, but if I don't know the size of my data set, what should it be?
X dot
N, right, in general. Yeah, X dot shape, that is also correct. What you are trying to say is correct, but we have, I think we have defined d comma n as X dot shape. Okay, so we'll use n here. So alpha init is this. Now, one more thing that we have to take care of is the bounds. Okay, so SciPy provides a way to do this. It has one method called bounds, and all that you need to specify is the lower bound and the upper bound, right? So bounds lb comma ub. So what's the lower bound here for alpha?
0.
0, right? And upper bound is
Infinity, I guess.
infinity. That's right? So we just have np dot infinity. So that is the bounds. Okay, so now SciPy, rather optimize has a method called minimize. What are you minimizing? You're minimizing the function f. We're using the initial value alpha in it to start with, and we are using following bounds. Does it have bounds or does it have constraints? It has bounds. Now the bounds are going to be following. Okay, let me write this down in three separate lines so that we see clearly what these values are. So this is the result of the optimization. I'm going to call it result. So is this part clear what we have done? SciPy needs some initial value to begin with, and we have initialized it to zeros. It needs to know what objective function we are optimizing or minimizing. In this case, it is f, which we computed here. So f is in terms of alpha, right? Alpha is the variable over which we are trying to minimize. And finally, it also needs, in this case, our problem has constraints. And the constraints are in the form of bounds, okay? And the bound is 0 on the lower side and infinity on the upper side. Okay, now we are going to run it. Okay, there is some error. F is not defined. I think we forgot to run the cell. Okay, so that is the result of our optimization. So many things are there. We don't need to get confused about all these things. The only thing that matters is the value x. So x, according to SciPy, is the variable over which we are optimizing. For us, that is alpha, but the object that SciPy returns is always going to have x as the variable. Okay, so way to access alpha optimal is in this way, right? So alpha optimal is, it turns out to be this 20-dimensional vector. Okay, is everyone clear about how we optimized the whole thing before moving on? Any
So I have
questions?
a doubt
Yeah.
here. So like instead of using SciPy, can't we use the argmin or argmax the way we like minimize or maximize things?
Okay, so argmin will give you the minimum over an array, right? So it will give you a minimum over an array of values or the index corresponding to the minimum, but it's kind of a discrete thing, right? So np dot min, let's say np dot argmin, as you say, will give me a discrete. It's over a discrete space. Okay, so
Okay.
it will give me that index 2 is where the minimum occurs. But what
Yeah.
we are trying to minimize is a function over a real space, right? It's a continuous space over which we are trying to minimize.
Okay. Okay. Yeah. Got
Okay,
it.
so any other questions?
Could you repeat what res.x does?
So res.x, so res, what it does is it just returns the output of your optimization problem, and it's not a simple output. There is a lot of information inside it, right? It's an object. So what is the type of this object? Let's see. So it is optimized result. So some class optimized result is there, and rest is an object of that class. Okay, so first thing, that is what it does. Now this object has a lot of attributes and values corresponding to it. So rest.fun, for example, is going to return the value of the objective function at the minima. Okay, so it's the optimum value of the objective function. Likewise, rest.x, what it is going to do is it's going to return the argmin of the objective function.
Okay, all right.
Okay, so rest alpha opt, let's just comment it here so that the argmin of the minimization problem. Any other questions?
So here we are minimizing it, right? So like we are not multiplying with -1. So only the function value will matter, or any other, because the bounds are limited as 0 and infinity for minimizing.
Yeah, good point. So we are not changing the bounds, right? So what we are changing is only the sign of the objective function, and therefore max becomes
Okay,
min.
got it, sir. Yeah, got it, sir.
Okay, any other questions on how we optimize this function? Okay, that's good. So once we have the optimal value of alpha, we are going to call this alpha star. Okay, so let's call it alpha star for consistency. Okay, alpha star is alpha 1 star, alpha 2 star. There are going to be 20 values as we have seen here. These are the 20 values. Interestingly, what we note is that a lot of them are zeros. Okay, a lot of the alphas are zeros. And recall that W star is nothing but sigma alpha star x y. Okay, so this is what we obtain by optimizing this unconstrained problem, right? So W is sigma alpha xi yi. So W star is, as a consequence, sigma alpha I star xi yi. Okay, so if so many values are going to be 0 for the alphas, W star is actually what we call a sparse linear combination of the training data points, right? So from this it follows that this definition follows, we call a data point, a training data point, a support vector if alpha I star is greater than 0. Okay, so this is how we arrive at the entire notion of support vectors, because if alpha is 0, then that particular vector doesn't contribute to W star, so it's not supporting W star in any way. So support vector by definition is a point for which alpha is greater than 0. Okay, so we'll ignore this complementary slackness for now. It's not, it's important, but don't worry about it. Only thing that you need to keep in mind is every support vector lies on one of these two supporting hyperplanes. And every point which is not on the supporting hyperplanes will necessarily have alpha equal to 0. Okay, is the idea of support vectors now clear? Computationally, support vectors are those values for which this alpha is non-zero. That's the main thing. And all of them lie on these two supporting hyperplanes. For example, these two are candidates, these 4 points are candidates for being support vectors.
So I think the third statement is valid only for the linearly separable case, right? Every
Yeah,
point.
we are correct. So what we are doing now is hard margin SVM, which is hard margin linear SVM, where the data is linearly separable. Okay, so we'll come back to the slide, but only after we have found out the support vectors for our problem. So we have alpha, right? So let's first look at when alpha is great. Okay, not alpha, it should be alpha star. I'm doing control F9 so that all cells are run. Okay, so alpha star is greater than 0 for some certain number of data points, right? So what are these data points? I can go and index into my data matrix. The columns are going to be my data points. So sorry, what did I do? Did something wrong. Okay, alpha star is greater than 0. Okay, so here's a problem. How do we get the data points from corresponding to these
X
integers?
colon comma alpha star.
X colon.
Colon comma alpha star greater than.
Okay, this is what we did before. What we did before. Boolean index did not match indexed array along dimension 1. Dimension is
So
2.
maybe try running all. Sometimes it gives an error.
Okay. Control F9. Okay. So good point. Okay. I don't know why somehow X got changed in between. Okay. X got changed here. You are right. Okay. So this has 22 data points. Don't worry about that. But thanks for that. You are right. So X got changed in between. Okay, so these are our support vectors 2, 5, 1, 2, 0, -1. Okay, so these are actually points in the data set X. If you notice 2, 5 is here. That's a support vector. What else? 1, 2 is also a support vector. We'll visualize this in some time, but where is 1, 2? 1, 2 is somewhere here. Let's take the last point, -3, -8, right? So -3, -8 is somewhere. I think this point, right? -3, -8 is this last point. Okay, so we'll come back to this, but our data set, our training data set has how many support vectors? 6 of them. Okay, so it has mistake. So you might also experience this problem when you're doing this collab. So don't run an individual cell. That is always going to be a problem because some later cells would have also run in the process. If you run the entire collab and the value of X gets overwritten. Okay, so always run the entire collab. Control F9 is the way to control 9 is a way to run the whole collab from the beginning. Okay, so there are 6 support vectors that we have, and these are the ones that we just saw. Okay, any questions so far regarding the support vectors? Okay, so I hope there are no questions. In that case, we'll move on. So what we have been looking at so far is called the hard margin linear SVM, right? It's a linear SVM because we are looking at linearly separable data. We have not used any kernels per se, and it's a hard margin case, right? Linear because no kernels, no nonlinear kernels have been used, and it's hard margin because it is linearly separable, right? So in your sklearn, what happens is all this happens internally. Okay, so you do CLF equal to SVM of whatever, and then CLF dot fit of x comma y. All this happens in the background. Okay, so this diagram just summarizes that whole process. You give a data set as input to your SVM solver, and then it solves a quadratic programming problem and returns your alpha star value. And from your alpha star value, you compute W star. Those alpha stars for which, those values of alpha star for which are non-zero, those points correspond to your support vectors. Okay, and prediction is simple. You just take the sign of W star transpose X. If it is greater than or equal to 0, you predict 1. If it is negative, you predict -1. Okay, so that is hard margin SVM. One final step, two final steps before we move on to soft margin is computing W star. Okay, so W star. So can someone tell me how to do W star if you have alpha star?
Alpha star into x into y.
Yeah, so we just apply this formula of xy alpha star, right? So xy alpha star, we will just plug in that x, that is W star. Let's first see what W star looks like numerically. 3 comma minus 1, okay, very close to 3 and -1 because this was designed that way. So it is actually 3 comma -1, but because of some precision errors, you get 2.999 whatever. Okay, so we have obtained the optimal weight vector, the weight vector for which the maximum margin will be obtained. Okay, so now let's plot the decision boundary along with the data points. I'm going to copy this scatter plot here. So this is the scatter plot part. Let me just, this is the data set. I'm plotting the data set here. And following the data set, you are now going to plot the model. Okay, the model here is the SVM. So how do we plot the model? It's of the form W of 0, W transpose X equal to 0, right? So W of 0 into X plus W of 1 into Y equal to 0. This is the model. So if you want to plot it using NumPy, what you need is, you need a set of X values and corresponding Y values. So let's first get a set of X values. Let's say it is np.linspace of y comma y. So corresponding Y values will be y equal to minus W0 by W1 into X, right? I'm just doing I'm moving things to the other side and dividing by W of 1. So Y values corresponding to this will be minus W0 by W1 into X. And since this is a line plot, I'll just do PLT of plot X comma Y. Let's try this and see. Okay, so you see that you have a nice looking decision boundary, but we can't stop here. We also need to verify if our support vectors are actually what we have found. So this is our decision boundary. Now let's go ahead and plot the supporting hyperplanes. So they are what? They are of the form W0 into X plus W1 into Y equal to plus or minus 1, right? So it's either plus 1 or it's minus 1. So when I begin with let me retain the same value of X, but Y now becomes, what does Y become? Becomes minus W0 by W1X plus 1 by W0 W1. Is this clear what we have done? Not clear, please stop me. I have plotted one supporting hyperplane, but for whatever reason it's not passing through the green points. Why is that? I need some help here. So can someone figure out what is the mistake we have made?
I think y equal to 1 minus.
Okay, so I have
In the
done
brackets, sir.
where? See, I've just taken x to the other side, so it becomes minus w of 0 x by w1. Okay, so that's all I have done.
There should be bracket this slope rate. Minus W0 by W1, that should be in the bracket, right?
Okay, that shouldn't matter, right? Ideally, if you use, okay, let me add it. But ideally, that shouldn't matter, I guess. Yeah, let's see. I'm missing something because your see, these 2 points should lie on the green line, and these 4 points should lie on the orange line. We are off by a bit.
Take the supporting hyperplane equation.
Sorry?
Supporting hyperplane for the equation of y, shouldn't it include 1?
So the supporting hyperplane should be what? W transpose x equal to plus or minus 1, right? So it's W naught x plus W1 y equal to plus or minus 1.
Sir, W star is our optimal vector, right?
Very good. That's a very good point. Thank you. That's the error. She's a very good find. Okay, so it's everywhere. It should be W, not W, but W star. Let me go ahead and change it. W star should be W star. Should also be W star.
Sir, I think you might have missed another W star
Ah,
on
you're
line
right.
11.
Line 11, is it? Okay, thanks.
Yes, sir.
Super. Okay, so that is what the mistake was. W. Thank you. Right. So W star. Right. So let's now compare this with what we had here. So we had six support vectors. Right. So notice that these are the 6 support vectors. 4 on the green side. 1, 2, 3, 4, and these 2 on the red side. Okay. So they necessarily have to lie on these supporting hyperplanes. All the other points have alpha equal to 0. So I can add a new point here, a new green point here, and that won't change the decision boundary. I can remove one of these red points or green points that are not on the supporting hyperplanes, and still that won't change the decision boundary, right? So that's why this algorithm is called support vector machines, because of the importance of these support vectors. Okay, any question in the decision boundary plotting that we did? Just some scatter plots and line plots. That's all we did. Any questions? Okay, so if there are no questions, we'll move on to soft margin. Soft margin is neat extension of hard margin for data that is not linearly separable. Okay, so typically you could have this scenario arise in two cases. One, It's not linearly separable because the structure is not linear. So could be quadratic. So your decision boundary could be quadratic, for instance, or your data points could be like circles, right? So they could be distributed around the circumference of circles. Okay, so in that case, you can't use a hard margin SVM any longer because the data is not linearly separable. But this non-linearity is structural, okay, and it can be solved by using kernels. Kernels, we looked at it quite deeply in the current run. For those who are from the previous runs, please have a look at the lectures, right? So that will give you an idea of how the kernels. Of course, we had looked at them briefly in the previous run, but here we spend more time on kernels. Now there is another type of outliers, that is your statistical outlier. So something like this, right? This red point here should actually lie on this side, but it does happen to be here on the green side. So that is an outlier, and we have to somehow deal with it. Any question? Someone is unmuted. Any question? Hello, I seem to be getting a noise. Is it from my side, or does anyone else hear this noise?
No, no.
No,
Please.
sir.
Okay, thank you. Right, so this kind of outliers cannot be solved by hard margin SVM. So we need what are called soft margin SVM. So ideally we want W transpose XY to be beyond 1, okay? But it's not true for this red point and this green point. So what we do is we add what is called a slack variable, or a bribe as we call it, okay, and we push them to the side that they should belong to, okay, and the moment we add this cost psi I to each data point, we also have to include it in the objective function. So this parameter C is a hyperparameter that controls the effect of these bribes on my model, okay. So this is the soft margin problem. So if you want to have an idea of what this IA is, if the point is correctly classified, if it lies on the right side of the margin, then the IA value is 0. If it is on the wrong side of the margin, then it has to pay some non-zero bribe, uh, non-negative bribe rather, to go to the correct side of the margin. So it's actually this distance of the data point that it has to cover so that it can reach the right side of the margin. That is what the IA means, okay. So any questions about the formulation of soft SVM? Okay, if not, we move on. So the dual for the soft SVM, just like we had a dual for hard SVM, it's pretty close to the hard SVM dual. So the soft SVM dual is going to look identical in a lot of respects. Only change is that instead of having just a lower bound on the alphas, you have an upper bound also. And interestingly, this upper bound is not some arbitrary value, it's this constant C. Okay, so the dual for the soft SVM is very similar to the dual for hard SVM. Only change is that the constraints are now bounded, the alphas are now bounded on both sides. And if you think about it, in 2D space, this constraint will be in the form of a square, right? So a square region. So in the case of 1D, 0 less than alpha less than C is an interval. In the case of 2D, this constraint is in the form of a square and hence called box constraints. In 3D, of course, this will look like a cube, okay? So, and that's the reason they are called box constraints. So we go back. Any questions, or shall we continue with this? Just need to find a way to optimize this function subject to these constraints.
Sir, if the data point lies between the two hyperplanes, then also it pays bribe, right?
Yeah, if it lies in between the margin or anywhere on the wrong side of the margin, it will have to pay a bribe.
Yeah.
Okay, uh, so can someone tell me how we'll solve this? If you stare at this code, what change should we make to this code so that we can solve the soft margin problem?
Bounds, you can provide the
Bounds.
bound.
Okay, right. So as simple as that, all that we need to do is we need to change the upper bound from infinity to C. Okay. So we are not going to waste time rewriting the whole thing. So we'll conveniently copy the whole optimization process. Few other things that we need to copy, they are this Q value and this Y value, right? All these things we have to copy. Let's copy them one at a time. So first thing is the Y value, right? Once you have Y, then Q will be Y transpose X transpose XY, correct? That's right. So Y transpose X transpose XY, and something you want to minimize in terms of alpha is what is that? You want to minimize
X at the rate Y.
X at
Q
the
equal
rate.
to.
Yeah, thanks. This is X at the rate Y. Alpha is minus alpha dot sum because that gets added. This is alpha transpose Q transpose alpha by 2, right? So that is what F is. So 0.5 into alpha transpose Q alpha minus alpha dot sum, that is the function F. Y we have defined from the data. Q F is there. Let's move this import to the beginning because that's, yeah. Any question?
Return keyword is missing in function.
Thank you. That is
Alpha transpose.
alpha transpose in this case is not needed because alpha is in NumPy. This is just a NumPy vector, right? So
Okay.
it will kind of figure it out on its own. Okay. So this is C. You have to fix a C. For now, okay, so this is all this we have to do. Now the question is this. Okay, plot the decision boundary and the supporting hyperplane for the following values of C. So we have to actually try it out for 4 C values, which means we have to solve 4 optimization problems. So the whole thing is going to go into a loop. For C in 0.01, 0.1, 1 and 10, right? 0.01, 0.1, 1 and 10. Do the whole thing again and again, right? So we'll have to optimize 4 times. And we'll also have to plot 4 times. So what we are going to do is we are going to copy this. It's probably not the most efficient thing to do, but okay, let me do the following. Let me see if we can just make it turn it into a function. So what does it need? Every time we need to give it a value of, so X is going to remain the same, Y is going to remain the same. Okay, just to be safe, let me give it the data set X, the label Y.
Star.
It also needs W star. Is there anything else that it needs? Let me also give it the C value so that I can title my plot appropriately. Let me title it as C equal to C, right? So, okay, so this will do my plotting. So from alpha star, how do I compute W? I compute it as W star is equal to XY alpha star, right? So X, Y alpha star. And I plot. So I plot by giving capital X Small y stands for the label vector, if you recall. And then xy, w star and c. Okay, so this is what we need to do, but we need to do this in a subplot, right? If you recall on Friday last, the NumPy matplotlib session, we saw subplots, right? plt.subplot. So we are going to do that. plt.subplot 2, 2, subplot number, right? Subplot number equal to 1. I'm going to start from 1. Subplot number 1. And every time I plot, after I plot, I am going to increment my subplot number. Okay, so shall we run this and see if it works or not? Let's run the whole thing so that if there are any other errors, we'll get to know. Okay, so what are the errors? This ran successfully. This has some error. Okay, alpha is what? Okay, so you see, I think the problem is with n, right? So n is here not 20. N is not defined at all. Do you see the problem? What the problem is? Okay, since this is also important, can anyone tell me what the issue is actually here?
Put n equal to 20 and check.
Okay, see, yeah, that's right. So the problem is the original, the hard margin SVM, we were working with a data set of size 20. Okay, so I had defined n there right at the beginning, and then I didn't redefine n for the soft margin case. Okay, so I should have done this for the soft margin case also, and I forgot to
But
do that.
n will have the value anyway 20, right?
Yeah, n will anyway have the value 20, and that is why it's giving this size 22 is different from size 20 error. Right, q is actually 22, but so let's just run that part alone. Q, if you look at it, q dot shape will be 22 cross 22, but n will actually be 20. Right, so that is the source of our problem, and we'll fix it by right below the data itself. We'll fix it. So okay, so I've added this. Now I'll run the whole thing again. Okay, so yeah, so it has solved the same problem 4 times. Okay, for different values of c. So can you now observe these 4 plots, subplots, and tell me what's happening? Are you able to make any inferences?
With the increase of C value, the margin is decreasing, right?
Correct.
And
That is what.
also with the increase of C, we are paying less bribe.
Correct. So we have made 2 correct observations. With the increase of C, the margin is becoming smaller. Also, with the increase of C, we are kind of, as a consequence of the margin becoming smaller, we are paying lesser bribes, or we aren't penalizing these. The penalty is kind of becoming smaller for these points. All right. So these are 2 observations. So let me go back to the slides and let's quickly look at why this is happening. Okay, so there is The last term, those who did SVMs, you'll be more familiar with this hinge loss formulation. Of course, this term also we did it, but last term I think we spent some considerable amount of time on the hinge loss. So this is equivalent to this.
Maybe, sir, if p-value increase, then hinge loss will be less. And it is balancing each other, means one if go up, other will come down.
Yeah, so yeah, in a sense, what we are saying is, if C value goes up, right, what we are telling the optimizer is that I'm going to penalize misclassifications, or rather margin violations a lot. This is a margin violation, right? I'm not on the right side of the margin. Only then this will turn up in the first place. Okay, so when you increase the value of C, then you are saying I'm very serious about violating margin. So that's why if you see if C equal to 10, then the margin tries to become as small as possible so that margin violations go down. Okay, so C equal to 10 has that effect of being a very strict person who doesn't want bribes at all, right? So no corruption if C is very high. Okay, so that's
So how to decide like which SVM is like the doing best?
That is a hyperparameter, right? So C is a hyperparameter. So you will
Yeah.
typically do some grid search or some method, some cross-validation method to determine what C works for you. So you will look
So
at the
for this data set, like how to decide? Because here we can already see like four different margins we're having.
okay. In this case, I can't decide using this data set because this is the training data set, right? So it is just for demonstration purposes. Ideally, we shouldn't be doing this point of picking the C based on the training set. So the cross validation should happen on some validation data set or some part of the training data held out for validation. And then on that you will choose C, whichever gives you the good classification accuracy. For example, that's one metric, right? On good validation accuracy, that value of C could be chosen. Okay, so that is respect to choice of C. Okay, so coming back to this, there are two terms in the objective, right? One term controls the width of the margin, which is this norm W squared by 2. So smaller the value of norm W, wider the margin. And the other one is the hinge loss, right? Wider the margin, larger the loss. Okay, because more number of points will pay bribes if your margin is wide. And this is exactly the plot that we obtained and just demonstrated it here. So 1 and 2 work in opposite directions. Okay, so if your margin is wide, then I'm going to pay more penalty in terms of bribes. They work in opposite directions, and C is the one which controls how much of one loss should I have and how much of the other should I have. Okay, so these are some conclusions. If C is small, we are fine with a wide margin, as is demonstrated here. And if C is large, we prefer a narrow margin. And if C tends to infinity, then you kind of reduce to the hard margin case. You sort of come down to that. So you can know for C equal to 10, you can study the number of support vectors the model has. I am not going too much into this. This is kind of left as an exercise to you. So please figure it out. That is the end of the SVM, soft SVM, and with that, the end of one part of what I wanted to say. And there are some closing remarks that I would like to give. Before that, any questions on this SVM part? Soft SVM, any questions? Either in the code? Yeah. Please go on.
When we are obtaining this W star, generally we have seen key this is a sparse prime vectors, means sparse matrix.
Right.
Sparse data set for W star. If I do not get this sparse data set, means very less zero, will this indicate something? Means my assumption, my calculation is something going wrong. I mean, wrong direction.
Good point. So you're saying, what if my alphas are not sparse? Is that what you're saying? If the alpha is not sparse, then what will happen is what you're asking, right? Is that what you're asking?
What will happen? No. Whether I'm doing in right direction or not. That I just what?
Okay.
Is
So
there any indication?
not really, right? So see, if you look at SVM, you can apply it to any kind of data set. The only thing is that if you don't get a sparse combination, it means that the data set is in such a way, right? So for example, we can very quickly cook up an example here where you will not get any, you'll have no sparsity at all. So for example, we have a lot of time, at least 20 more minutes we have. Let me just have this particular data set where you have, let's say, okay, 2 zeros 1 point, 5 0, I want everything on the y-axis, let's say, 2 0, 2 5, 2 10. Okay, so this is one set of data points. Let's say these are positive data points, and -2 0, -2, -3, -2, -10. Okay, so these are, let's say, negative data points. This will be just y equal to np dot array of, okay, so this is going to be your new data set. So I don't know how much this will work, but let's try it out. I also don't know. Okay, physics. Okay, there's a transpose, right? Does alpha star look like? Okay, so where is alpha star? Okay, so alpha star here is. Okay, I'm looking at a way to make all of them support vectors, right? So that will kind of answer your question. So what I'm saying is, if all points are support vectors, which is perfectly possible, right? If you have everything lying on the supporting hyperplane in some sense, can you think of a data set that will achieve that? I thought this itself will give us that, but it seems it's not giving us that.
To parallel line, I think.
Sorry?
If we draw like two parallel line.
Right. So these are two parallel lines, right? So
yeah. Okay.
Maybe it should be exactly.
You can use the data point that was asked in the end.
Sorry, I can use?
We use the data point that was asked in the end. If you know that there were 5 points, the same thing we could draw.
Okay, you can use the data points that were obtained as support vectors in the last case. Is that what you're saying?
Yeah, the data points that were, like, I meant the ones that was there as the final SVM that we answered in the end term, the 5 points that were there, you can directly use those points.
Right. That's a good point. That's a good point. Okay, let me just pick those points and see what happens. So where are those points? These are those points. So let's go back. Okay. This is okay. Is this correct? Can you mute, please? Or is not muted? Okay, so that's a good idea. Let me just very quickly figure out what the labels were. Where are those points? I'm sorry for those who are still watching. This has to be sorted out. You have the labels to kind of get this working. So 1111 minus 1 minus 1. Okay, so those are the labels. Let's go back to this now. So this is the data set and this is the label. Okay, type it out. 1111 minus 1 minus 1. Okay, so strictly speaking, as you said, should give us all 6 as
So you'll have to make it transpose X dot transpose.
okay, so what I did was I copied that thing itself, right? So I copied that
Okay.
X dot transpose itself, right? So okay, thanks. I think whoever pointed it out, knew the whoever. It's a very good suggestion. So this is what we get, right? All alphas are first one. This is not at all sparse. So does that mean that we are on the wrong direction? No, it doesn't mean that we are on the wrong direction. It's just that for the particular data set that we have obtained, all the points contribute towards making your weight vector. And but typically in practice, I don't think you will observe this, right? You will have a lot of sparsity in your alpha star, and only few points which are close to the decision boundary will contribute towards the weight vector. Okay, but yeah, but that's a good question. I'm not sure. I can't give you an entirely sure answer because in practice I don't know how these things will turn out. But if the alphas are not sparse, then the only thing that I can conclude is that that's the data set's problem, right?
So the question is, sir, when the alphas is not zeros, that means if all the points falling on the hyperplane, then if I just little squeeze my plane, then all points becomes very good, means well classified. I just try to understand between these 2 points. As you said, when all the points in on the hyperplane, fine. So now if I squeeze my hyperplane a little, then all the points, the alpha value becomes 0. I just try to understand between these 2.
If you do what, alpha becomes 0?
No, now as the alpha value is not 0, that means all these points lies on the hyperplane.
Correct.
Now my decision boundary having say x distance, say 1 unit away, the hyperplane is right now in this position. Now all the points fallen on this hyperplane. Now if I squeeze my hyperplane a little, so instead of unit distance, I make my hyperplane 0.5 apart from the decision boundary. Now suddenly all these points become very viable, means well classified. The alpha value becomes 0 now.
No, right? How they will still contribute? No, I mean not all of them will contribute, but if you are just going to uniformly move them this way or that way, the geometry doesn't change much, right? So the whole point of they being support vectors is this, right? So let's say instead of where is that? Instead of 2, let me just perturb one of them. Let me make this 2.2. Okay, let me make this 2.2 and see what happens. What happens? See, I think this is the point that I made 2.2. It still kind of contributes, right? So, sorry, I didn't get the point still.
Oh, sir, if you go to this thing where you have 4 diagram of the decision boundary along with hyperplane.
Yeah.
Yeah. Now suppose say all the points in the hyperplane means all the red and green point distributed in between this green boundary and this orange boundary. Okay.
Okay.
Now, if you move your hyperplane little towards the decision boundary in this condition, then all the values means alpha becomes 0, right? In this case.
Okay, so that is where I'm a bit hesitant to look at it that way, because you don't have control over the decision boundary, right? That decision boundary gets fixed for the optimal decision boundary is fixed by your data set. It is the boundary is a result of solving the optimization problem on the data set, right? So you don't really have the liberty to move it arbitrarily, right?
Sir, I think he's talking about like changing the value of C, and then like in this case we have seen, like if you increase the C, the decision boundary will like move moving towards each other, I think.
Oh, okay. If it is C, yeah. If you change C, then yes, you are controlling the width of. I mean, you are playing around with the width of the margin, and therefore things will either go closer or move apart from each other depending on what you do to C.
Exactly. Now, sir, actually, sir, I have the control only in C out of this whole equation, right? So
Yeah.
uh,
Right.
so when I am seeing all the points are lying on the hyperplane, now little increase of C means I am in safe position.
Okay. Right.
And I just try to understand in this way, because this C is equal to 0.01 or 0.1, it will depends on the situation. Now, how one should give this value? Only by experience or seeing something from the model's outcome?
Oh, okay. See, as I said, right, this we should not look at. See, ideally, you can't even look at an image like this, right? In the real world setting, your data set, your feature space will be like R100 or something, like 100 features you will have. So you will not have access to this image at all. First thing. Second and more important reason is that C cannot be determined by the models. In any of these plots on the training data. C is chosen using the validation data, right? You do some kind of cross validation. You do, let's say, a grid search or whatever method, right? Leave one out, leave 5-fold cross validation, whatever method of choice. You try out different values of C and choose that one which gives you, let's say, highest accuracy on the validation set. Okay, so that is how you actually choose C in practice. You can't choose C by, visualizing what happens to your margin, because the feature space is not at all going to be R2, but it will be R100 or R200 in practice. Right? So what we have done is for a toy problem, just to understand
Yeah,
what
I
happens.
need to do some more permutation combination with other things. Then only things will be clear. Okay.
Right? Yeah. So in practice, what we do is we don't have just C, but if you have some kernel also, we'll have to choose the parameter for that particular kernel. For example, if you are using RBF kernel, then you have to choose that gamma value, or if you are using polynomial kernel, you have to choose the degree of your polynomial. All these things are hyperparameters which you tune. Okay, so it's that. I have some closing remarks on the whole idea behind the workshop, with which we can kind of stop. So the three main points is these are the main points. So everything cannot remain a black box. Okay, so we can use sklearn It's very important that we need to learn sklearn, but perhaps sometimes it will help us, to go back and learn NumPy also. Okay, so sometimes it's necessary to peep inside the box, which is the main point behind this workshop. Even though we have standard sklearn classifiers, like what sklearn offers, or there's something called libsvm, which is a very popular method to do SVMs, right? But still, sometimes it's good to peep into the box and try to understand what actually happens. Okay, and sometimes it's also necessary to build your own box. Okay, we have done something like this in these 3 days. Okay, even though we have well established libraries which do classification, we built our own classifiers in some sense. Okay, so this is the summary of the idea behind what we did. Okay, at the same time, we must know where to stop or when to stop. Okay, what I mean by this is, we want to build a model. Ultimately, we want to train a model on some data set. Okay, that is our goal. So what we did this time was we took NumPy and we showed a preference for NumPy over sklearn because we wanted to peep into the box. We wanted to build our own box. So you can keep going, right? So why stop with NumPy? NumPy itself is a black box. So I can open that black box and say that I want to do everything in native Python. I don't want to use NumPy arrays at all. So I will build my own NumPy. I could have said that. Or you can go even further and say Python is a high level language, and no, I'll do it using C. Or you could be even more weird and say that assembly language is more closer to the machine than C. Okay, so the end of this process is to build your own computer and do all the other things. Okay, so this is taking things too far. So you must know when to stop, that is when to open a box, and when to keep the box closed and then use it as a model, right? And use it as a black box and go on with life. So this is something we can't teach because this is something we are also learning in the process. But you must know how to do the first 3 steps. You must know when to do the first 3 steps. You must also know when to hold back and not do the first 3 steps. Okay, so those are some closing ideas about the workshop. So any other questions? If not, I think just give me 1 second. If you have any questions, go on and ask. But just give me 1 second.
Sir, will you be sharing the slide for the SVM?
Yeah, SVM slides, I'll upload it in the same drive folder. Okay, so yeah, 1 second. So is by any chance are Anamika and Nitin there in this call? Anamika, Nitin, are they there? So okay, so yeah, so on their behalf also, I thank all of you for your presence, and hope you all learned uh, something interesting in these 3 days. Okay, so the assignments are there. I think you have access to the course, MLT workshop course, and you can submit them. The deadline is Wednesday, I think, but in case you need some more time, we can even extend it. So we'll take care of that.
Sir, on behalf of
Need
all the
more
learners,
workshops like
participants,
this.
we want to thank you, sir. It was
Yeah,
really very helpful. Yeah.
thanks a lot. Yeah.
Need
Okay
this
then.
kind of workshop.
There, like other boosting algorithms and logistic regression and softmax, will it be another workshop for those? Like,
Okay, so there may not be. Okay, actually, it would have been nice to cover all of them. But see, we kind of covered it during the course, right? So one thing
yeah,
that you can do is you can go back and look at the solve with instructor sessions for uh, the SVM, sorry, not SVM, the MLT course this time. So you will be able to find it there.
We'll need the collabs. We don't have the collabs.
Okay, yeah. So collabs, what we'll do is we'll upload them after the assignment deadline for this
No,
workshop.
for other topics, not for these algos. I'm
Yeah,
talking
so
about what was taught during the course.
right. Yeah.
For
Those
the,
collabs are currently hidden until
okay.
the workshop gets over. So once the workshop is over, we'll release it. Okay, so
For all the algorithms, for all the
10 weeks, 10, 11 weeks of the course, you can
okay,
ask
okay.
your juniors for that. If they, I mean, one of them should have access, right? So if not, we'll share it. Okay, so
Right.
that it's actually a common link. It's accessible to everyone in the program. Okay, so it's just a matter of sharing the link.
Right, sir.
Okay, so yeah, just 1 minute. Yeah, I think that's about it. We can. Yes, I'm just waiting to see if there's something else we need to discuss. Yeah. Which one?
Sir,
Yes. Any question?
If everyone is done, then I have some common questions. Yeah?
Okay. Yeah. So just one. If it's just 1 second, I just need.
Yes.
Yeah. Yes. Kumar. Yeah. Yeah. You can go on.
Yeah. So generally, sometimes we have seen that if we don't solve the problem in the linear level, then we go at higher level. Like that, sometime in the k-means or the concentric circle type of if distribution is there, then better we do the kernelized and we take it higher level to make it separate.
Correct. Yeah.
Yeah, it is certainly also possible that we can solve this without going at higher level also. If we remodified that the scaling of the coordinate system, then that thing can be separate on the same dimension also.
It's not just a question of scaling, right? For example, if you have circles, right? If your data is on one class is on, say, the circle x square plus y square equal to 1, and other is on some other larger circle,
Right,
then
right.
no matter how you scale,
Yes.
you'll maybe turn circles into ellipses, but you will never be able to separate them linearly, right?
Uh, uh, we can separate linearly also.
Using the same x1 x
Uh,
features.
yes, yes, yes. No, so what I did that at the end, this is the equation type of thing. One is the x square plus y square is 1. Another is equal to radius equal to 5, let's say. So there is a two circle is there. So at the end, data is and the point only, no? So if we square that both coordinate, then it will separate automatically linearly.
Sorry, I didn't get that part.
Yes. So suppose we have a two concentric data on the space somewhere on the plane, and data must have the one point. Suppose it is the two-dimensional point,
Okay.
then obviously there will be x and y coordinate of the each data. There will be two coordinate. If it is the data is scattered wave, means data I'm talking about as a point.
One second, I'm kind of. So the reason I'm kind of preoccupied is I just want to know if I should close it now or we can continue the discussion. But
Yeah. So we can close. So
yeah.
I
No,
will with the
no, not because of you. I just want to know if I have to close it or someone else is joining or not. Once I figure that out, I'll. Okay, yeah. All right. So just 1 second, Kumar. Yeah. So others, yeah, we are done. Okay. Thanks for your comments. We are done with the workshop, and you can now.
Thank you, sir.
Yeah. Thank you.
Thank you.
Yes. Yeah. With that question from Kumar, we can.
Thank you,
close.
sir.
Yeah. So Kumar, you can go ahead. What is the question?
Yes, I have sent that one code. What I wrote that for that purpose, but I think this code is not
Okay. So what?
properly.
Yeah. I think it will be easier if you can you create a post on.
Yes, sure.
That way we can.
Right now, only I will post that.
Yeah.
I will try.
I use a polar coordinate system, like
No need to use. Yeah, no need to use polar coordinate. We can use that, but generally without polar system also we can use. And it's become the two different area, and that area will be separated on that same plane itself.
Okay.
Okay. Right. So this around we'll discuss in.
Yeah, discourse will be fine.
Course,
Yeah.
right?
Yes.
Okay, then. Yeah. Thanks for joining. We'll formally close the workshop. Okay.
Thank you, sir. Thanks for the workshop.
Thank you.